Hey guys, welcome back. We're on Chapter 8, an Introduction to Metabolism. We're going to hit this chapter just very briefly. It's kind of an introductory type chapter. We're about to start talking about cell respiration and photosynthesis, and those are all metabolic pathways. And we're going to find out that metabolism is all about how the living organism transforms energy, takes energy in one form and then creates it or recreates it, transforms it into another form and uses it. So this chapter is kind of a hodgepodge of information. It actually goes to some physics, and unfortunately, if you were not a big fan of the chemistry material we covered earlier, it also goes back to a bit of chemistry. So I'm going to briefly hit this chapter. I'll try not to talk too much because I'm already late in getting this to you. And the quiz that you're about to take for Chapter 7 and 8 only has a couple of questions, I think about 6 questions from Chapter 8. This is information that we will hit in the future and kind of wrap into all the other subjects as we go. So here's our basic overview. So far we've been talking about like the cell membranes and all the various jobs that the cell organelles have. And of course, if you're going to be doing work, whether it's biological work or mechanical work, it's going to require some input of energy. And so this overview talks about that just a little bit. The living cell is a miniature chemical factory where thousands of reactions occur. And I think I said earlier, perhaps online on the forum, that biology is nothing but very complex chemistry. So chemical reactions play a big part, and especially chemical reactions that are all chemical reactions that release and or store, create, and transform energy. So the cell extracts energy from its surroundings through various ways, and then applies that energy to get work done. And this energy could be in the form of heat, it can be in the form of motion, it can even be in the form of light and sound. All of these are energy transformations. So living creatures are basically energy transformers. They take in energy, transform it to another method or a form of energy for their own purposes. A good example are these two squids, or the kind of outline of these two squids that you see here. These two squids have the ability to bioluminesce. In other words, they take in energy in the form of food that they eat, just like almost all living creatures do, and some of that energy is used to perform a chemical reaction that creates light. So there are a few creatures that can do this. The squid, lightning bugs that you may think of on a summer's evening. So there's a couple of different insects and creatures that have this ability to bioluminesce, or they are bioluminescent. In other words, they can use biological chemical reactions to create light. So that's just one kind of interesting example of energy transformation. Concept 8.1 says an organism's metabolism transforms matter and energy subject to the laws of thermodynamics. So this chapter is interesting because it's talking about biology, of course, but it's also mentioning physics and chemistry. So we're kind of throwing a whole bunch of science together. A quick definition, the word metabolism is basically the totality of an organism's chemical reactions. All the various chemical reactions that output energy and input energy, all that together would be considered metabolism. And metabolism is another one of those emergent properties of life. Metabolism is this overall scheme or this overall process that you don't see in a particular one molecule or something to that effect. It involves a huge number of molecules, a huge number of cells, a huge number of organs, and it's a type of emergent property that you see higher up in the chain of organization. The word metabolism comes from the Greek metabol, I believe. I'm not sure if I'm pronouncing that right, but it looks like metabol or metabol, and that means to change. So metabolism is all about change. Within the cells and within a living organism, things are very structured and very organized, and they have to maintain that structure to maintain life. So we have what's called metabolic pathways. A metabolic pathway starts with a specific molecule and ends up with a specific molecule. So it starts with a specific ingredient, you could say, and it ends up with a specific product at the very end. And each step along the way, it may be 1 or 2 steps, or it may be 50 steps, each step is catalyzed by a specific enzyme. We're going to find out what enzymes are coming up. So I want you to think of a metabolic pathway as a roadmap from one specific location to another specific location with scheduled stops along the way. And there may be 4 or 5 stops along the way, and each one of those stops is a reaction or a process that is catalyzed by a particular enzyme. So of course I'm a Corvette fan, so I threw the little Corvette in here. So you can imagine that we're starting with a particular molecule A, and we have 1, 2, 3 steps, and we're going to reach molecule D, which is our end product. And every step along the way requires a chemical reaction, requires an enzyme to accomplish this. And we start out with A, and we change as we go, and we end up with a final product here. This is what metabolism is. This is a metabolic pathway, starting with one and ending with another specific product, usually multiple steps along the way. We describe these pathways in two different terms. One of the pathways is called a catabolic pathway. A catabolic pathway releases energy, breaking down complex molecules into smaller compounds or simpler compounds. So like digestion. When you are digesting whatever you had for breakfast or lunch, that is a catabolic pathway. Your body is taking large polysaccharides or large long-chain molecules and is breaking them down. That releases energy. So cellular respiration, which is what the cells do after you've digested your food, cellular respiration is the breakdown of glucose in the presence of oxygen, and that's a good example of catabolism, depending on how you want to pronounce it. So catabolism or man, I can't say that word. Catabolism. It's a catabolic pathway. That's the breaking down of complex molecules into simpler ones, which releases energy. The opposite of that would be anabolic pathways, and perhaps you've heard of like anabolic steroids. An anabolic pathway requires energy. It consumes energy, so there has to be an input of energy, and it's a building process. It's building more complex molecules from simpler ones. So when the cells inside are creating proteins, when the ribosomes are taking amino acids and building longer, more complex proteins, that is an anabolic pathway. That's an anabolic process. Overall, we can think about this as something called bioenergetics. Bioenergetics is just the overall study of how organisms manage their energy resources. Some of those are processes that require energy. Some of those are processes that give off energy. All together, this kind of study of this is called bioenergetics. A bit more physics here. You're probably familiar with what energy is or how to define energy. Sometimes it's easy to know what it is, but it might be difficult to define it to someone else. Energy can be defined as the capacity to cause change or the ability to do work. And of course, energy exists in a wide variety of forms. Some of those forms are very convenient or conducive to doing work, particular types of work, and some of them are not. So, for example, we're going to talk about a lot of different forms of energy, heat being one of them. Heat is a form of energy that is not really capable of performing a lot of specific types of work. But there are other forms of energy that we'll discuss that can get work done. So here's a quick review from maybe IPC, Integrated Physics and Chemistry, or if you've had any physics before, you've probably studied this, no doubt. Kinetic energy is the energy with moving objects. A baseball being thrown through the air has kinetic energy. Heat, or thermal energy, is the kinetic energy of random motion of atoms. So heat is also a type of kinetic energy, but we're talking about just the random motion of air molecules or air atoms or other atoms or molecules. Potential energy, this one is usually a bit more difficult. Potential energy is not the energy of motion. It's the energy that a material possesses because of its state or its location or its structure. A sandwich has stored chemical potential energy because of the chemical bonds in its molecules. A gallon of gasoline has chemical potential energy. A rock sitting at the top of a mountain has potential energy due to its position and to the fact that gravity can pull it down. Chemical energy is the potential energy available specifically in chemical bonds. So, for example, in that gasoline or food. And, of course, energy can be converted from one form to another. You've probably heard of this idea that energy is not created or destroyed, the conservation of energy. But certainly it can be transformed from one type of energy to another, and it can be moved from one object to another, or from one organism or part of an organism to another. Remember those squids turning potential chemical energy into light. That's a good example of energy conversion. The squids are taking food molecules which have stored chemical energy, and they are using that in part to create light, which is a different form of energy. A quick little animation for review. So if you want to right click and hit play, it kind of goes over all the different kinds of energy. It does a pretty good job of kind of hitting the basics. Another quick picture here showing different kinds of energy: potential, kinetic, this is some basic physics information, and if you didn't study physics at all, of course you might want to spend more time on this, but if you had studied some physics in 8th grade or IPC, something like that, you're probably familiar with this. So take a look at this, and if you need more information, certainly give me a shout or a post online and I can help you out. Living creatures in biology has to comply with the other laws as well. So just because we're talking about living creatures, it doesn't mean that there are not chemical and physical laws that apply. So the laws of physics apply to living creatures just like they apply to non-living creatures. So we want to discuss that just a little bit. Thermodynamics, you've probably heard that word before. Usually we think of thermodynamics as studying the motion or movement of heat, thermal energy, but in reality, you can talk about thermodynamics as basically the study of energy transformation or the motion of energy altogether. In an isolated system or a closed system that's isolated from its surroundings, we're going to find that's a little bit different than an open system. So you can have an isolated system. So here their example is liquid in a thermos that's kind of isolated from the rest of the environment. Or you can have what's called an open system where energy and matter can come in and out. So when we're talking about living creatures here on planet Earth, you need to keep in mind that we're going to be talking about an open system. Living creatures are an open system. They're constantly taking in energy from the outside, and they're getting rid of waste products. So there are things coming in and there are things going out. You can actually think of the entire Earth as an open system. It's obtaining a steady stream of energy from the sun, so it's not closed off from its external environment. It's an open system, and that's pretty important. So let's talk briefly about the laws of thermodynamics, which are laws of physics, and they do apply to living things, and they do apply to the Earth and living organisms. And keep in mind that we said that the Earth and living organisms are open systems, and that will help you understand how these laws apply. So the first law of thermodynamics says that the energy of the universe is constant. The total amount of energy or matter in the universe is thought to have come into being at one point during what we kind of think of or call the Big Bang. All the details of exactly how that occurred, of course, are still a mystery. I mean, science thrives on these questions where we don't have all the answers. And if you're going to be a scientist or if you're going to be a scientifically minded person, you have to be okay with that. We're likely never to have all of the answers, but that doesn't mean we don't know a lot. We do know quite a bit. So all the energy of the universe is thought to have been created, you could think, in the Big Bang, at the initial formation of the universe. And that is constant. So what that means is energy cannot be created or destroyed, but it can be transferred and transformed. So when the electric company is creating electricity and sending it to you, in reality, they're not creating energy. They're transforming energy from one form into another form. And the form they're transforming it into is electricity, which is convenient for a wide variety of uses. But they didn't create energy. All they did is transform energy from one kind into another. So the first law is also called the principle of conservation of energy, and that's something you've probably seen and heard quite a bit, that energy cannot be created or destroyed, simply transferred and transformed. Sometimes when we talk about a reaction or we talk about a physical activity, we say that energy is lost. I want you to make sure that you understand that it's not truly lost. It doesn't disappear. It's not gone forever. When we say energy is lost, we usually just mean that it's become non-useful. Usually that's heat or sound, something like that. So when you are pedaling your bicycle, not 100% of the energy that you are putting out goes into moving the bicycle. Some of it is lost to friction and heat and sound, and we might say it's lost, but it's still there. It's just not going to move the bicycle. So it's kind of unuseful or not used for our intended purpose. So the first law of thermodynamics is usually one that people understand, that energy is not created or destroyed, it is conserved. The second law people get a little confused about. And the second law says that every energy transfer or every energy transformation is not 100% efficient. And so it increases what we call entropy or disorder of the universe. So this second law helps to explain why a perpetual motion machine will never work. A perpetual motion machine is one of those that once you put it into motion, it stays in motion forever because it is 100% efficient. Well, that is not possible in our world as far as we know. That breaks the second law of thermodynamics, for one. So that machine, no matter how efficient, will lose some energy. Again, I'm not saying it disappears. I'm saying that energy is lost and becomes heat and things of that nature that are not useful to do the work that the machine is doing. So this idea is that every transaction is not 100% efficient, and you lose some of that energy to what we call entropy, which is basically the disorder of the universe, is the random motion and movement of the atoms and molecules of the environment. So let's kind of talk about those two laws as it relates to biology. Let's take a look at this little bear chowing down on this fish. So here is this bear. He's eating what looks like a salmon. That salmon has stored chemical energy in its body, and he is eating that salmon. So we said that energy is conserved. That salmon got its energy by eating probably other smaller fish who probably ate plankton, who got their energy from the sun. So that energy is transformed and transferred, but it's never disappearing or never created. The fish didn't create the energy that is in its body. It got it from somewhere else. And now the bear is going to get that energy. He doesn't create the energy. He gets it from eating the fish. So the first law of thermodynamics is there is not a gain or loss of energy in total. There's simply a transfer of energy. The second law has to do with increasing entropy. So there was a certain amount of energy in that fish that the bear ate, and it would be great if 100% of that energy would go to, say, move the bear forward when he's running here. But that doesn't happen. The bear is not 100% efficient. He loses heat, which becomes non-useful energy. He gives off waste gases and other materials. So he is creating, or he is increasing the entropy of his surroundings. The air around him becomes less ordered because he has added energy and heat to that. So he doesn't get all of the energy from the fish. He gets only a certain amount, a certain percentage, and the rest of it is going toward increasing the entropy of the universe around him. This process of increasing entropy is kind of a natural process that occurs without energy input. In other words, this is kind of the natural state or the natural way of things. This spontaneous process, you could call it. And by spontaneous, I don't mean it happens quickly or it happens all at once. I just mean it happens naturally. It happens without the input of energy. So living cells, as they are using energy, they unavoidably lose some of that energy. So for a process to occur without energy input, to increase the entropy of the universe, it doesn't take extra energy to add in to do that. That is a spontaneous process that happens automatically. So think about water flowing down a hill. That's an example of a spontaneous process. Think about the decay of a roadside armadillo from a living body to a pile of mush. That is a spontaneous process. The rusting of an old automobile is a spontaneous process. These increase the entropy of the surroundings, and they are automatic functions that occur without the input of energy. They are what we would call a spontaneous process. They are energetically favorable, in other words. So here is a bit of a question or a problem. If the basic nature of the universe is to increase entropy, to increase disorder, then how does biology work? Because cells work against entropy. They create order. They build complex molecules out of simpler molecules. And we have this order and function that we see in living creatures that kind of goes against this law of entropy, this second law of thermodynamics, it seems. So organisms oftentimes create more structured molecules and other things that would seem to go against this entropy. Now you have to keep in mind that organisms also do the opposite. They also take large molecules and break them down into smaller ones. So they do both. They go against entropy in some cases, and they go with entropy in other cases. So energy is always flowing into an ecosystem and out of an ecosystem. And in some cases that is going with entropy, increasing disorder. In other cases that's going against entropy. It is creating order. And so we need to talk about how can that occur. Does that not seem to break this second law of thermodynamics? So take a look at these two things. Here we have, looks like a sea urchin, or the shell of a sea urchin, part of a sea urchin, and some particular type of plant. I'm not sure, it looks like some sort of cactus type plant. But look how organized and structured it is. They are taking in different sorts of molecules and then using those molecules to build very complex, very structured and organized systems. Well, doesn't that break the law of thermodynamics? Doesn't that go against entropy? Well, let's find out. To answer this question, you have to remember what we said about living systems are not closed. They're not isolated from their environment. They are open systems. The evolution of a more complex organism does not violate the second law of thermodynamics because those living systems are open. They are constantly being refueled from energy from the outside environment. So you can have an increase in organization in an organism or a local area as long as the overall entropy of the universe is still continuing to grow. If you look at the universe as a whole, entropy is still increasing as a whole. But that doesn't mean that there can't be pockets of increasing organization, and that could be representative of the Earth or the living creatures on the Earth. So again, entropy or disorder can decrease in an organism or a system, but the universe's total entropy is still increasing. Another good example is, say, for example, the disordered water molecules or droplets can form complex ordered snowflakes. If you look at a snowflake under a microscope, it is far more complex and ordered than a random water droplet is. But that doesn't mean that the second law of thermodynamics is broken just because that snowflake formed. You can have local examples of increasing organization. That does not mean that the entirety of the entropy of the universe is not still increasing. As a matter of fact, some scientists think that the universe will end in what we call the heat death of the entire universe. If you want more information about that, click on that link. That would be where eventually all the energy of the universe is spread out so evenly that there are no pockets of increasing order, and so we have reached maximum entropy and we are at an equilibrium, which would mean basically death of the entire universe. So not a happy thought, but I don't think it's going to happen this week. If you want to click on that link right there, you can get more information if you were interested in finding out about that. So when scientists are studying, or biologists are studying reactions, chemical reactions that occur, oftentimes they want to know, is this a reaction that will happen spontaneously? In other words, is it one of those reactions where it will go kind of automatically on its own without an input of energy, say from the cell or something like that? And sometimes it's difficult to tell. So what they have to do is they have to determine what are the various energy changes that are going to happen. And you can find out whether or not a reaction will occur spontaneously or if it's going to have to be helped along with extra energy input. The way you find out about this is by looking at something called the free energy of a system or the free energy of a reaction. And it's called oftentimes Gibbs free energy, and we use the capital letter G. That capital G is for J. Willard Gibbs, who in 1878 at Yale University helped define this idea and function of free energy. And this free energy is basically the energy that is available to do work. So the portion of energy that is available to cause change or do work in a system or in a reaction is what we call the free energy. Now, I don't want you to panic when you see formulas like you see down here at the middle of the page, physics formulas. We're not going to get heavy into physics, but I just want to show you the formula and describe what we're talking about here. So this formula for calculating the change, the little triangle, the delta means change, for calculating the change in free energy is related to a couple of things. It's related to what we call the change in total energy, capital H is representing total energy, minus the temperature, that's going to be measured in degrees Kelvin, and the change in S, which S here is standing for something called entropy. Entropy and enthalpy are two words we're going to take a look at. So entropy. Remember, entropy is the amount of disorder, basically. Enthalpy is the total energy. So total energy of the entire system is called enthalpy, this word right here. And the amount of disorder or disorganization is called entropy, and that's represented by the S. So these two words oftentimes are kind of confusing because they sound a lot alike. I don't want you to worry too much about this formula because we won't be using it directly. I just want you to know that what this formula tells us is that a process, only a process with negative change in free energy is spontaneous. In other words, what we're saying is you can only step down. Only the process that will step you down in total free energy left over is going to be spontaneous. And that kind of makes sense. Think about it in the way of, say, stairs. A ball will roll down stairs on its own, and every level that it falls, it has less energy than it did the previous step higher. This will happen naturally, spontaneously, but the ball will not go up the stairs. It will not gain free energy, and it would gain free energy as it moved up the stairs. That will not happen automatically or spontaneously. So basically all this formula shows us is that if process has negative change in free energy, that would make it spontaneous. Otherwise, it will not happen on its own. So we said free energy is the amount of energy available to do work or cause change. It's kind of a measure of an object or a system's tendency to change, how stable it is. And if it has a lot of free energy, it's not very stable. It has a lot of possibility for change. And when we have a spontaneous change, we are lowering that instability. So we are losing some of that free energy. The free energy is going down, and the stability of the system is going up. Eventually, we would reach a state of what we call equilibrium, and that's a state of maximum stability. So at equilibrium, you have the lowest amount of free energy, but the highest amount of stability. And that's pretty important to realize because a process can only be spontaneous if it is working towards equilibrium. So a process is only going to occur on its own if that means you're giving up free energy and gaining stability. And once it reaches that equilibrium, it's going to stay put right where it is because that's the area of maximum stability and lowest level of free energy. Here's a couple of different examples. Here's one that involves gravity, gravitational motion. So here, up there on the high diving board, the person has a higher G, higher free energy. It's less stable, more capacity to do work. Then you have this change. As he's falling through the air, he is losing free energy or giving up free energy. There's a negative change in the total amount of free energy, and is reaching a more stable state down here below. Same thing with diffusion of molecules. Same thing with this chemical reaction. You have greater instability, greater free energy, and then you reach a state where you have less available free energy but more stability. This idea of free energy can be used to look at some of the chemistry involving biology. And again, I think the best way to think about it is like that stair step, like a rubber ball on a stair step. If you were to stand on the banister above a set of stairs and drop a ball from above, and it landed in the middle of the set of stairs, would that ball naturally move up the stairs or would it naturally move down the stairs? So naturally, after the bouncing, it would move down the stairway. That is this spontaneous process where it is losing free energy every step down, but it is gaining stability. That is what would naturally occur. It wouldn't naturally move up the stairway. Now, you could get it to move up the stairway by throwing it that direction, but you would have to input energy. And every stair it went up, it's gaining instability and free energy. When we talk about chemical reactions in metabolism, we can define them in a couple of different ways. We can call them exergonic. Exergonic, think about the word exit, means that energy is being released or is leaving that particular system or reaction. This is spontaneous, energy going outward. It's a spontaneous effect. Or a spontaneous reaction. The opposite of that is endergonic. Endergonic requires an input of energy. It is absorbing free energy from the environment, and it does not happen on its own. It is non-spontaneous. So exergonic is energy out, endergonic is energy in, which luckily the words kind of help you out there. So exergonic can happen on its own, endergonic cannot. It requires the input of energy. If you're a kind of charts type person, here's a quick little chart or graph to kind of help you out. This is an exergonic reaction where the reactants started with a large amount of free energy, and through the process a lot of that energy was released or given off, exergonic. The products are down here. They're at a more stable state. They have less free energy, and the amount of energy released right here was less than zero. In other words, the free energy available is now less than zero. So this means we went in a negative fashion. So the amount of free energy dropped or went down. And so we say the change in G was less than zero. It was somewhere in the negative. Down here we have an endergonic reaction. This one requires an input of energy. The reactants start with a low amount of free energy. Energy is put into the system, and the products end up here with a higher amount of instability and free energy, and this required an input. So the free energy available has gone up, and so the change in G is greater than zero. It's in the positive. Reactions in a closed system will eventually reach equilibrium, and then you're done. Everything will cease. But remember, cells and living creatures are not closed systems. They are never in equilibrium. They are open systems. There's a constant flow of new material in and old material out, and energy in and energy out. And that's kind of a defining characteristic of life, is this metabolism that's never at equilibrium. You have a catabolic pathway in a cell that releases free energy from a series of reactions, and you can kind of look at this. We'll look at an example like with a hydroelectric dam or a hydroelectric system, kind of like the stair step I was talking about. So let's take a look at comparing a closed system versus an open system. Here's a quick summary. Let's look at it in detail. So here would be like a closed system. If you started with a closed system, not open to the outside environment, yes, it would run for a while. As you see here, you have energy being released. So this would be like a metabolic pathway. This would be a catabolic pathway where free energy, the amount of free energy is going down, and that energy is being released. This would be exergonic. But eventually, we're going to reach equilibrium, and then that system stops. That system ceases, because now there is no change in energy from one side to the other. Compare that to an open system where there is a constant input on this side and a constant outflow on this side. In this case, we have a system that is constantly basically being refilled and never reaches equilibrium. It is exergonic. It is giving off energy, but it never reaches equilibrium, so it consistently runs. This particular model is even better because it shows all these different steps along the way. And notice with every step, you are giving up free energy. The change in free energy is negative, less than zero, and it's reaching a more stable state. But notice it's open both at the top and bottom. Think about this as a catabolic pathway, like cellular respiration, where your body is digesting food molecules and using that to create energy. So at the top we have oxygen and glucose. Oxygen came from your lungs, glucose came from whatever you ate, and that's being catabolized all along this pathway, broken down, and energy is being released. This energy is being used by the cell to do all of its different jobs. And then out the other end you have waste products, carbon dioxide and water. The carbon dioxide and water have less energy than the input oxygen and glucose did, and that is given off as waste product, replaced with new, and that process continues, never reaching an equilibrium. If you were to reach equilibrium, that would be your death. Let's pause right there. Go get a quick bite to eat so that you won't reach equilibrium, and then we'll come right back.